Hello friends, welcome back. In this session, we are going to learn more on quantization. But before we get into it, we need to understand that AI appears to be very easy at research level. The challenges get spiked up the moment the research turns to deployment phase. The production environment throws surprise challenges in terms of technical, operational, and ethical perspectives. It is never easy. The research by RAND Corporation indicates that 80% of AI projects do not succeed, which is double the failure rate of traditional IT projects. When developed and tested in the controlled infra, the AI models will provide significant success and high performance rates. But when moved to the real world deployment, the results will be unexpected, which could actually reveal the impact in efficiency, scalability, and fairness. We have to discuss what are the bottlenecks that are going to be troubling us in terms of the deployment. We also need to understand the key deployment challenges followed by the mitigation techniques. There are multiple bottlenecks that will come in terms of the concurrency issues, IO constraints, data transfer delays, hardware limitations, and last but not the least, model complexity. But there are strategies available which will help us to mitigate the performance bottlenecks. One of those is model optimization. It's one of the widely adopted techniques and it's going to be very interesting. Let's go ahead right away with the learning. Let's get into quantization right away. It is one of the most appreciated methods. This involves converting high precision models, normally which is actually FP32 format, to the lower precision formats such as int8 or FP16, which are often referred as half precision floating point. These lower precision formats are very useful and they substantially reduce model size and enhance inference speed while minimally affecting accuracy, because we cannot compromise accuracy for anything. Quantization is frequently referred and preferred technique because int8 models are considerably much smaller than FP32 models. The reduced size naturally leads to improved inferencing and requires fewer computational resources as compared to FP32. Additionally, these lower precision models are particularly very much beneficial for edge devices, where the computational capacity is often limited and is often challenging. One can consider a practical scenario involving a very simple image classification model, which is actually operating on an edge device, which can be Intel AI PC, which is equipped with Intel Ultra Core 5 processor. In the original FP32 format, the model might process an image in approximately about 200 milliseconds. But however, once you apply quantization, which converts it into the lower precision model, which is like int8, the same task could then be completed in around 80 milliseconds, which is going to result in definite latency reduction of 50% or above. The improved inference speed is attributed to the reduced memory consumption as well. When models are larger, such as those using FP32 precision, they require more memory and consequently they take longer time to execute. However, when you go ahead with quantization, these models can operate much more swiftly and with less memory usage. This enhancement makes them better suited for deployment on edge devices, which can be like drones or even smartphones. I've given you a very simple example, and this picture is again going to reveal you how exactly quantization is going to help you in reducing the model precision from FP32, which is high precision, to FP16, which is medium precision, to int8, which is low precision. That way, it's going to be very interesting. It is always interesting and important to learn things practically, which I have been stressing. And we will go ahead with the code right now. I am going to start a process where we will see a code, we will run through the code, where quantization can be performed and we will also see the result. The provided code in this section is going to help you in illustrating the process of training a very basic neural network using the well-known MNIST dataset, storing the trained model and then implementing quantization to enhance its efficiency and reducing the size is the task. The model is designed to identify handwritten digits, as you know, from 0 to 9 and is subsequently converted to TensorFlow Lite format for use on mobile or edge devices. It is one of the most preferred again. It is very simple and easy to understand. Through the application of integer quantization, the model's weights and activations are compressed to 8-bit precision, which can result in substantial reduction in file size while definitely preserving accuracy. The code which we are going to present you, which we are going to walk you through here, offers a super comparison in the size of the model, which is before quantization and after quantization. That way it's going to be very, very effective. You can see the code here. It's a very simple piece of code where in the first step, we are going to load the MNIST dataset, which has got the handwritten digits 0 to 9. Then, as usual, we will have to normalize the data. We'll scale the pixel values from the range of 0 to 1. Then, we will go ahead and define a very simple neural network model. As you could see, this is no complex model and we are using it in a very simple manner, where in the first stage, we are flattening 28 cross 28 images into one-dimensional array. Then, we are using the ReLU activation. Then, we are going ahead with dropout to reduce overfitting. And finally, we get the output here. It's a very simple neural network, right? Alright, so what next? We have to compile the model. Now, we will go ahead with the IDM optimizer and normally preferred and it is very efficient for the deep learning, we all know. Then we are going ahead with the training with one epoch. Then save the train model in the TensorFlow's saved model format. And we will go ahead with zip the saved model to measure its actual size. Followed by that, you will get the size of the zip model. This is all what is done in this simple piece of code. I have given the proper commenting so as to make you understand things in a much better way. Let's get to the next step. We will then define a function to generate representative data for the quantization. This way, we can get the model adapt to the typical input patterns. Then we will convert the original model to TensorFlow Lite format. We do it for a simple reason that the model, when converted, should be more suitable for edge devices, mobile devices, embedded devices. Then we apply the quantization. Then we use the representative dataset to guide the quantization process in a very simple way. Then we will go ahead with forcing the model to use the 8-bit integer operations. Then finally, we will convert the model and store it in memory. That's all. We have almost come to the end of the code. We will save the file, save the quantized model as a TensorFlow Lite file. Then we will measure the size of the quantized model. We can compare it with that. You can run this in any platform. We have preferred Google Colab. You can run it in the Intel Tiber AI Cloud. You can run it in any platform of your choice. It will work fine. So you can see that the quantized model size is 102.17 KB, before which the original model size was 1054.60 KB. So 90% reduction in the size has happened because of the quantization. Isn't it interesting? It's a very important technique where we can use quantization to reduce the model size, and optimization can happen very nicely here. This is one of the most preferred techniques. You can scan this QR code to get the code. I have also highlighted the link from the GitHub where you can take the code and try it out yourself. That way, you will see how exactly things work. And I hope it was interesting. If you like the channel, please subscribe. Thank you.